So, we have already discussed mean and variance in the first lecture, higher order moments and moments inequalities in the second lecture. Now, we are moving into the third lecture on generating functions. In this lecture, we are going to discuss three important generating functions, namely probability generating function, moment generating function and characteristic function. We will give the definition, some properties of these and then one or two examples. And later we will find out the generating functions for some standard distributions in detail. So, as such now we will give the definition and the properties and one or two easy examples. So, let us start with the third lecture, that is generating functions. In this we are going to discuss probability generating function. In short, it is PGF. The second, we are going to discuss moment generating function, that is MGF. The third, we are going to discuss characteristic function. This is also generating function. So, let us start with the first one, probability generating function. The definition: probability generating function. Let x be a non-negative integer valued random variable, that is basically a discrete type random variable. In particular, it is a non-negative integer valued random with the probability of x takes the value k, we denote it as a p suffix k, where k takes the value 0, 1, 2 and so on. There is a possibility it may take a finite number of values also. Then one can define the probability generating function as g suffix x as a function of s, that is nothing but summation probability of x takes the value k, s power k, where k takes a value from 0 to infinity, where s is the real variable which lies between minus 1 to 1. So, this is a real valued function, it is a function of s in the form of series with the probability mass at the point k multiplied by s power k. So, the right hand side is a series, the left hand side we are denoted by the g suffix x as a function of s. Since the right hand side is a series, this series converges within the interval mod s less than or equal to 1. We are not bothering about whether this series is converges or not outside this interval. What we are saying is within the interval s lies between minus 1 to 1, the right hand side series converges gives the function of S, that is called the probability generating function of the random variable x, where x is a non-negative integer valued random variable. That means whenever x is a non-negative integer valued random variable, one can define the probability generating function as a function of S. We will go for a few remarks, then we will give some examples. As a remarks, the first remark, since I said that the right hand side series is converges between minus 1 to 1, if you substitute the value S is equal to 1, you will get the summation of probability of x equal to k, that is nothing but 1, because that is a probability mass function. So, this value is going to be 1. The second remark, you can relate a probability generating function with the expectation of a function of random variable. That is, the probability generating function of x is same as the way it is a summation of probabilities multiplied by s power k. One can write it is nothing but expectation of s power random variable x. Third remark, one can relate the probabilities with the derivative of a generating function. Suppose I define the generating function with the bracket r of the function of s is nothing but rth derivative of generating function, probability generating function with respect to s. Suppose I define g suffix x bracket r is the rth successive derivative of a probability generating function with respect to s, where r can take the value 1, 2 and so on. I can write down rth derivative evaluated at the point 1, that is nothing but expectation of x into x minus 1 multiplied by x minus 2 and so on till x minus r plus 1. The way I defined g suffix x bracket r at 1, that is same as expectation of x into x minus 1 multiplied till x minus r plus 1. The right hand side is called factorial moments of rth order. Sometimes if you want to find out the variance, you can find the factorial moment of second order. Through that you can find the second order moment or variance. Similarly, I can find from the probability generating function, by taking the derivative, I can get the probability mass at the point k, that is p suffix k, that is nothing but the probability of x takes the value k, that is same as the kth derivative of probability generating function evaluated at the point 0 multiplied by 1 divided by k factorial, that is going to be the probability of x takes the value k. Here k can take the value 1, 2 and so on. After you get the kth successive derivative of probability generating function, substituting value s is equal to 0, multiplying by 1 divided by k factorial will give probability of x takes the value k. So, this result is by knowing the probability generating function you can get the probabilities, whereas the definition says if you know the probabilities you can get the probability generating function for a non-negative integer valued random variable. Let us go for finding the probability generating function for the random variable which is of a non-negative integer valued. Example 1, let x be a discrete type random variable with probability mass function p of x is equal to k, that is n c k p power k 1 minus p power n minus k, where k takes a value 0, 1, 2 and so on till n, where n is a positive integer. Otherwise, the probability mass function is going to be 0. So, this satisfies the properties of to define the probability generating function. So, one can go for finding the probability generating function for this random variable. So, g suffix x as a function of s is nothing but by definition probability of x equal to k s power k summation k is equal to 0 to n n c k p power k 1 minus p power n minus k s power k. So, here the p values is lies between 0 to 1, that I did not specify earlier. And if you see the summation, this is always converges. Summation k is equal to 0 to n c k p power k 1 minus p power n minus k into s power k. So, you do not need to expand and then do the simplification. P power k and s power k you can keep it together. Then it becomes a p s power k 1 minus p power n minus k. And this is nothing but the binomial summation. Therefore, one can easily write p s plus 1 minus p the whole power n. By combining p power k and s power k, you can easily get the result p s plus 1 minus p the whole power n. That is going to be the probability generating function for this random variable. Later we are going to introduce this random variable as a binomial distribution with the parameters n and p, or with the parameters p and n. P is lies between 0 to 1 open interval, n is a positive integer, then the probability generating function is ps plus 1 minus p whole power n. Now, we move into the second generating function, that is a moment generating function. In short, it is a MGF. The definition is as follows: let x be a random variable such that the expectation of e power t x exist for t in some interval including 0. So, as long as expectation of e power t x exists for t in some interval which includes 0. In that case, one can define the MGF or moment generating function of the random variable x as is a notation m suffix x of t, that is nothing but expectation of e power t times x. Since I have written expectation of e power t x, e power t x can be expanded, therefore, you will get that is same as that is same as 1 plus t divided by factorial 1 expectation of x plus t square by 2 factorial expectation of x square and so on plus t power n by n factorial expectation of x power n. Since we said expectation of e power t x exists, therefore, all the moment of order n exist about the origin, and this series also converges. Then only one can find the MGF of the random variable x. It is a function of a t. If fewer moments exist and other moments does not exist, one cannot define the MGF of the random variable. As a remarks, the first remark, one can get the nth order moment from the MGF by successive derivative of moment generating function n times with respect to t, then substituting t equal to 0. One can get the nth order moment about the origin from the moment generating function by successive derivative n times with respect to t, then substitute t equal to 0. That is same as expectation of x power n. The second, if two random variables are having MGFs are same for all t, if two different random variables whose MGFs are same for all t, then one can conclude both the random variables are having the same distribution. This result is valid for the probability generating function also. I have not mentioned. If two random variables probability generating functions are same for all s, then both the random variables are having the same distribution. Let us go for the example finding the MGF. Let x be a continuous type random variable with probability density function f of x is 2 times e power minus 2 x when x is sliced between 0 to infinity, 0 otherwise. The same example which we have taken earlier for finding the mean and variance. Now we are finding the MGF of the same random variable. That is nothing but MGF as a function of t, that is expectation of e power tx, that is same as minus infinity to infinity e power tx f of x dx. Here we are doing with the assumption that the MGF expectation of e power tx exists, then we are finding the MGF. Substitute f of x is 2 times e power minus 2x between the interval 0 to infinity, and after simplification you can get the answer, that is 1 minus t divided by 2 power minus 1 whenever this result is valid when t is less than 2. That means the e power tx is a finite quantity for t less than 2. Then only you can define the MGF, and that MGF quantity is going to be 1 divided by 1 minus t divided by 2. So, this is a very important, not for all t between minus infinity to infinity the MGF exists. For this random variable the MGF exists between minus infinity to 2, and the MGF value is 1 divided by 1 minus t by 2.